Okay, so hi everybody. We have a guest, Chen, who is a computer music PhD student in the music department, and he will talk about some of the work on transformers. And I will let Kay introduce himself in a little bit more detail, where he's from, or the background and the research. Okay, so please, Kay.
Okay, thank you, Shlomo. Okay, hello everyone. My name is Chen, and I'm the first year computer music PhD student at music department in UCSD. But okay, in fall I will be like second year. And before here, I completed my bachelor's study degree of the computer science in Fudan University at Shanghai, China. So here today is my honor to be here to present a very novel music transformer paper, which is done by Google. Magenta is a place that full of full of creation about music, and what about the detail of this paper has been shown in the footnote here. It is Chen one about music transformer generating music with long-term structure in ICLEAR 2019. And so here's my outline for this paper. So we will first go into very basic ideas about the stem stones of the music transformer from the recurrent neural network to the self-attention and to the transformer. And then we can go into how Magenta, the Google creation institution for music performance representations and music transform, because how they encode as a token about the music is very important when we fit this input into the transformer structure. And then we will review some code implementation and examples. But to be sure here is that the code implementation is what might think of the music transformer does, but actually many people will think about this music transformer structure very differently. So this is my code implementation, and then it's done summary. So before we go into the detail about the music transformer structure, I think we can first show you some examples of the music transformer. So here you can see there's about pages about Magenta in Google. You can just type in the music transformer in Google, and then we will first click it in the first pages is here. So like I will show you the very famous example produced by Music Transformer here. So this is the what the Music Transformer create the music. So there's a prime here. The primer is the original music does, but after this very short primer, you will see their generation. And there you can see many arrows, the colorful arrows here, like the yellow, the pink, the purple. It actually denotes that when they create this kind of generation, what kind of things they are considering here in the previous sequence. So we can see first listen to these kind of things. So can everybody hear that? So can everyone hear that? Okay, so we can just repeat it. So this is a very short demo from Music Transformer. There's a creation for music. So you can just judge that what this kind of music, classical music looks like and hears like. You can see like what Music Transformer does is a little bit predicate for the music. So here we go into the detail of the Music Transformer. So what this kind of paper, the Music Transformer paper does, there are two contributions of it. The first contribution is very clear. They implement the structure of the music, the transformer structure, which is the latest, very efficient structure about in the deep learning in the music generation. But to be sure here is that it is not promised. The not promised here is that actually no one knows how they encode transformer into the generation. There are many ways using transformer in music generation depending on different scenario of the task, different encoding of the representation, and different structure you're using. Like for example, you use the transformer encoder or transformer decoder. You use the masking or not masking. So Google did not provide any code structure detail for the music transformer, so no one knows that. But they only provide the Colab, which is a cloud console of their server about music transformer. You can use their pre-trained model, and then you input your primer of your demo music, and then they will continue writing and generate the music. But you can just only use their pre-trained model. The detail of the model is hidden in their server. You can luckily like download their parameters, and you expect to use the TensorFlow to load this parameter, and then you recreate this kind of like the graphic path in their neural network. But it cannot be possible because they use a TPU, it's not GPU. So you cannot use this node in GPU. So finally, you cannot know the structure. This is the first contribution. But the second contribution is that not many people will have this kind of concern. Many people will ignore it because they actually do a very good memory complexity improvement in the relative attention matrix. We will introduce about the relative attention in later pages. And actually, the relative attention is not what the Google's produced, but it's from another paper in 2019 in NASL in NLP area. But actually, they use very high cost memory cost, memory space. But this kind of paper actually reduces kind of space into a very short memory. So we will go into this kind of things for that. So we'll first go into the first one is RN, the recurrent neural network. So what is RN? Is like we have the input we call X1, and then we feed into a structure we call RN, and then this structure will output the hidden size, which is called hidden vector, which is called H1. But they will produce H1. The first line is going to leading layer or other layer after that, and you can just output your Y1. This is your first output. So you give you X1, you can get Y1. In another space, the H1 will iteratively go back into the RN again in the same structure, and then you feed in the X2, and then you got Y2, and you got H2, and into the RN again, you got X3 and Y3, then produce iteratively like the recurrent method. So for each time when we create the Y2 here, Y2 here, or Y3 here, actually they will consider the X3. X3 is like the accumulation from the X1 input, X2 input, X3 input. So actually, if you produce the Y3, you will consider about the H1, H2, which is the previous sequence. If you produce the Y2, you will consider Y1, Y2, H1, H2, H3. So this kind of structure actually has the memory, what we call the utilization of the previous input in the sequence. So if you know like you want to say something, for example, I love you, and then if you want to predict the number and the words you, actually the model will consider I and love, these two words. So actually they will utilize the previous input, and they can even control the time to forget some parts of the words and to restore another one. So this is what we call like the long short-term memory, or we have new structure. It's like the stage 2 version of the RN we call STM or GRU. So this layer is advantage of the RN, but disadvantage is very clear because even though they can control the time to forget to build a short memory, but they cannot control the distribution of the contribution. For example, like if we want to create a word, say you, and they cannot tell what this kind of confidence is from like I or love. I mean like For example, if you see the I, you will produce the U. But actually, like, maybe like the model is seeing like, oh, there's a love here, so we produce U. So the model cannot know, you cannot know what model think like what kind of things is most important when we consider I and love in producing the U. They cannot like times the times this kind of probability together to output the value like it's like merging all the things together. And the second thing is that the training cost is of the RN is very high. I mean, like if you want to produce a sequence, you should fit into X1 in the first time, and then X2, X3, X4, one by one. So the training is the one by one. So if you want to fit it like the 1024 sequence, 24 length sequence, you should like loop it again about like 1024 times. So it's a very high train cost. So what attention does is a little bit different. So attention layer is not like loop again. It's not an iterative layer. So you input X1, the X1 will become three things. The first thing is Q1, we call the query. The second thing is the K1, we call key. And then it's about the V1 is value. So all the things can be input in the same time, simultaneously, so we can produce what Q2, K2, V2, Q3, K3, V3, Q4, K4, and V4, etc. And they can be input in the same time. And then we can think about what is query. Query is that we have a number, and then we want to search for the leg table. So if you have the Q1 here, you will time the K1, K2, K3, K4, and become an A1. So A1 is not one number, A1 is the list. It's a list about like the Q1 times K1, Q2 times K2, Q3 times K3, for example here. And then we can know like this kind of thing is just like the probability. I mean like you use the query and use the key and time together. Actually you got something is like how many I should consider for the first one, how many I should consider for the second one, how many I should consider for the third one or the final. So how to convert the unnormalized number into the normalized one? So we can we use the softmax. So we take the softmax of the A1, and then it can become the probability. So here actually the A1 is the softmax after the list of the multiplication. And then we have like to erase it. So A1 is the list. So after we have the list, we have the probability. So we know like if we want to produce Y1, how many we should consider from the second one, the first X1, the second X2, the third X3, and the fifth X4, for example. And then we have to multiply A1, each number in A1 into each number into the K value. Then the value 1, value 2, value 3, and value 4. And then we can become the Y1. And the same things is going again and again in producing A2, Y2, A3, Y3, A4, Y4. So what's the difference between the attention and the RN? So the RN so if you want to produce the RN will have number have the X token into the structure, and then they will produce like the Y1. So if you produce Y2, they will consider the previous sequence. If you produce Y3, you will consider Y1 and Y2, X1, X2, H1, H2. But you cannot consider anything after after this kind of current stage. But the tension is different. So if you produce Y1, actually we can consider all the sequence. So the Y1 can be produced by, for example, multiply 0.5 about X1, about the V1, 0.25 times like the V2, 0.21, 0.1 times V3, etc. So each time you produce Y1, Y2, Y3, actually you consider the whole sequence. And then you can know how many things can be considered in each kind of space. For example, you consider 0.5 of the V1, the 0.3 of the V2, 0.25 of the V3, etc. So you can know each number exactly how many importance score in each kind of place. So this kind of things can produce very good performance. Then than the RN. So they can be used very often in nowadays many structure. So this is the things after we have the mathematical formulation and we can got the attention. The Q is the query, the K is the key, the V is the value. So each Q is actually when we take in the row is like we have the first input Q1, second input Q2, third input Q3, into like the fifth input Q5. So this kind of row at column is actually a dimension, so it's the hidden dimension. So you multiply the k is actually the same dimension of as the q, but you just take the transpose of it. You can just multiply in the matrix, and then you got the a1, and the a1 is actually after softmax. So you take each row and you take the softmax of it, and then you can know each important scores of each one, and then you times it in the value. So notice that here value is actually present in the row space. It's not in the column space. It's because like if you want to produce the output y1, actually you should consider like each value in the first place, and each value in the second place, and each value in the third place, and then you multiply different probability or important score of it, and then you can produce the y1, y2, y3, and in later. So each output of the same place y1 is in relation to the q1 and all the key throughout all the sequence. So that's what we see here is the softmax qkt divided by a normalized number and length times v. So this is the matrix multiplication here. So after we can get the y1 is our output, y2 is also our output. We can just get the whole sequence output. But there's one thing that we did not notice that. So in Rn, actually the sequence has the order, right? So we have the same example here. I love you. So I is in the first place, love is in the second place, and you is in the third place. But if you use the attention model, actually they will consider all the things, so they will not know what the position is not important, because even though you swap each position, for example, love are you or are you love, actually they will also consider important score. So the position is invalid in in the attention model. So how to add the tension with the importance of the position? So you can just add the absolute position encoding. The absolute here is that the first place is the first place. The second place is the absolutely second place. So we have 1, 2, 3, 4, 5. So in computer we have 0, 1, 2, 3, 2, and minus 1. So how we do that? We just add this kind of number into the key, and then we multiply it again with, and then we multiply again and add it together, and then we got the new softmax qkt divided by k. So here is the position encoding. We call it the p transpose. So the one here is not the real number 1. It's just like a random number, but you should confirm that in the same place the number should be the same. Usually we will use the parameter function like the sine, cosine as the position encoding of the specific number. So it's not the 1, 2, 3, 4, 5. It's like, for example, like 0.5 pi minus 0.5 pi minus pi, for example, 0 or something like that. So you can just input different number, but you should make sure that in the same place, in the same position, the number should be the same. So this number can also be get by neural network by using crossing the embedding layer. So there's many ways to get that. So different from like on the basis of like q times kt, actually you just times q times another variable called pt, and then you got the position a1, a2, a3, a4, and you add it together, then you can get the new one. So with this kind of new matrix of A, actually it is like the tension score, importance score with the absolute position encoding. So for example, when we take the picture as an example, is that in the previous time we add the x1, x2, x3, x4, But now we actually add another number. So x1 will concatenated by 1, x2 will concatenated by 2, and x3 will be 3, and x4 it will be 4. In the computer space like this 1, 2, 0, 1, 2, 3 for example. And they will add the position. So like each number. So if you swap the x1, x2, so like the content of x1, x2 is different, but actually the position will be also different. So if you take a look at it together, actually the x1 concatenated by 1 is the different from the x1 concatenated by 2. So if you swap the position in the whole sequence, so the final result will be different. So this is absolute positional encoding. So it's very easy because we just add the new matrix and using the calculation of the addition. But so there's another way to do that. Before we say about the relative addition, we want to talk to you another things that there's also another thing is different from the RN is because in RN we cannot see in the future, right? So if we want to simulate the attention model as the same as the RN, we have to ask the masking. The masking is that if we want to produce Y1, we should not let the model to see the K2, K3, K4 because they cannot see that in position 1. If you want to produce Y2, you should only consider about the Q2, K1, and K2. So we add the masking select the stairs from the first one, second one, third one, fourth one, and 5. So we can just add masking. The masking means that all the things will be masked as 0 or like the infinite number. So like the output will not consider the future input. And that's the things in the attention model how to simulate the RN. So we talk about the first thing is about the absolute position encoding. So each place, like the first place is 1, the second place 2, the third place is 3. But there's also another thing is the relative position encoding. So what is the relative position? It means like when we consider the Q1, we know like the Q is the 0, the 0 in the first place. But if we consider the Q2, we should make sure that the Q2 is also the first place, and the Q1 is the -1 place. So when we output each output, Y1, Y2, Y3, in each output, we should consider relative position. It means that when we output Y1, we should know like the Y1 is the first place. When we consider outputting the Y2, we should consider that, oh, we have the Y1. So Y1 is in the -1 place, and Y2 is in 0. And when we consider the Y3, we can know like Y1 is in -2 place, Y2 is in -1 place, and Y3 is in 0. So like the -3, the Y4 is -3 to 0, and the Y5 is -4 to 0. So in each output, we should know that the model should know like the relative position between the whole sequence of this kind of current stage. So the things will be a little bit hard here is because in each time when the query Q1, Q2, Q3 times the KT, the key, and add the position encoding will be different. In the first place, the Q1 times the KT, but the PT will be 0 and slash because in the final we should not know like in the final stage. And the second place, when we consider Q2 times KT, the position will be -1, 0. And Q3 will be -2, -1, 0, and Q4 will be -3 to 0, and Q5 will be -4 to 0. So that means that in each time we manipulate each and output each row of the position encoding of the relative potential, actually we should use the whole matrix of the PT into that. So we have the, for example, if we have like the L, like the 5 L is equal to 5, so we have the length of the L. So in the absolute position encoding, we just only need one L times D matrix. But here, each row will need one matrix. So we have L times D. So this is the huge memory here. So music transformer produce one method that can reduce this kind of L times D to LD. So we only need to use the LD matrix, we can finish the relative attention. So how to do that is that this is our beginning. So beginning will be Q1, Q2, Q3, Q4, Q5, and the K will be the same. And the final output will be this one. So what we need is that we need the Q1 times the 0 placed on the position encoding within the purple 0. And we need Q2 times the -1 and 0 in the position place. We call red -1 and red 0. Same here, the yellow -2 to yellow 0 and green -3 to green 0. And then, so how to transfer from this place into this place. This is our target. So in the previous one is that we have like multiplied the L matrix, because in the Q1 we multiply the matrix and then we got these kind of things, and then in the Q2 we multiply another matrix, we got the second row, and take an example. But here we have another way. The first one is that we just only need one matrix. This one matrix we call ET is D times L, because we transformed it. So the original one is L times D. And this kind of metric is that we have the final relative attention. It's -4, -3, -2, -1, and 0. This is the final stage of the relative attention matrix. This is the last relative attention matrix. And then we multiply by ET times Q, we can get this one, right? And then what matrix thing is beginning here. So we have this one. So we're padding in the left side. We reshape it here. This is like the L plus 1 times L. So we'll reshape it into the L times plus 1 here. You can know like this is the first row, and this will be the second row. This will be the third row, and this will be the fifth row. So after that, it can be transposed into this one. And then we deleted the first row and take the mask of it. You can get the stairs of the relative attention here. So we only need L times D matrix, we call E, and times Q, and use the NumPy or touch transpose function, we can get each relative attention matrix. So we reduce the L times D relative attention matrix to the L times D. That's a huge improvement. This is what music transformer does. So then we go into the transformer called the music. So what the Google present the music is that we have the MIDI. The MIDI is that we have like different notes in different time, and we have different duration of each note. It's like kind of like the piano sheet or like kind of music score. And then they use one thing to present is that we have 4 tokens. The first token is the velocity. It denotes that what kind of current velocity is in the current time. And the second one is the notes on. It denotes that when this time, this kind of notes will be on. And then it's about the time shift, is like the duration of the time. Like we shift the time, we move the position from the 0 to 500, and from 500 to 1000, for example. And then another one is notes off. It denotes that what kind of note will be off. So in the same time, we set the velocity to be the 80. And then we have the notes on in a 60. So this kind of note is begin. We shift the time by the 50. 500 is like 0.5 seconds. So we got here. We add another note 64, and then we shift the time again. We add another note called the 67. So 67, 64, and 60. Then we shift the time by 1 second here, and then we find like the 60, 64, and 67 is off. So we add the off token, and then we time shift again, and we set velocity, and then we have another node. So this kind of performance token can be used in the representation of the music in the polyphonic music. So the music transform is like even though we do not know what music transform does in detail, but according to many GitHub, um, the reproduction of the codes, we finally found that maybe they use the thing is that it's called the next token prediction. So the token is like the set velocity, nodes on, time shift, this kind of things, and then we just do like we input the token from 1 to n, and then with that model to produce the n+1 token. And then we have the token from 2 to n+1, and then we add the model to produce the n+2 token. So at this time, actually we have like we use the music transformer to do the next token prediction test. It's what we call the music generation. So the input here is the each token, like the velocity, nodes on, nodes off, time shift, and then we add the absolute position encoding and the relative position encoding. So this is what we call music transformer. So this is the whole structure, and then what it does is just like this one. So after I implement code, because we did not have the code from Google, so we have the codes here. Is that what we write? What I wrote around here? I just try to reproduce real code. So so the layers here, if you want to see the model here, is that we call the music transformer. And the music transformer is the masking attention layer model with the absolute position encoding and the relative position encoding. And then each kind of layer is the encoder, is the attention layer. So attention layer here is what we call the relative attention layer. So you can see there's the attention, what attention does. So yeah, you can see many things, kind of things as like the same in the attention model. But the difference is here is the schooling. The schooling is what we call, we pad the matrix in the left, and then we reshape it, and we delete the first line, and then we can got the S relative is what we call here. So like we pad and we reshape here, and then we reshape it again, and then we can just have the relative attention matrix, and then we just add the matrix into the attention process. Then we can got the relative attention model. And this kind of things only needs about like the L times D memory. It means that we don't need the higher memory. For example, like if L times D is 124 megabytes, if we want to times L again, maybe like the length will be like gigabyte, like 10 gigabyte. So like your model will be like the 10 gigabyte, so it's a huge model. But if you use this kind of things, you can just make your model to be like the 1 gigabyte or like 100 megabytes. There will be like the huge improvement in the memory space. So the code will be like here. So if you want to see my code in detail, so I can just share to you, just email me. And then it's about like the examples. So we have already seen the examples in the classical music produced by Google. But what about like if we can produce like another data set? For example, if you want to create a pop music, train by pop music and produce pop music, what will be looks like in the music transformer? So I did this kind of experiment a couple months ago. So we used the 900 and 9 about like 1,000 Chinese pop song, and we call it the Pop 909. This kind of paper is just accepted in IceMirror, a conference on music information retrieval, and then we train it by the about 100,000 pop songs, and then we produce just like we input a primer of melody, and then we let the model to continue writing the left one. So as you can see here, there are many checks here. So the red one denotes that this is the primer, so it is the original song. And the green one is what the model continues writing. So actually you can see that the difference is very clear about like the generation and the original song, but the the result, when you listen to the result, you can see like what the music transformer does is a little bit good. Okay, let's first take an example of the first one. So it begins to generate. kind of like first generation. So we can just see another example. For example, here we have so we can also see an example like just randomly pick like so here. So it's just like what the music transformer does in the pop music, but actually, like the generation is not as good as what the website created because like in Google, like they have like millions of data sets, but in the school or in our generation, in our experiment, we only have like a few data sets for like 100 song, 1,000 song. It's just less than like the million data set. So it means that the generation will be not converge very better, but actually we can just little see that there's the potential like power in music transformer that in creating music in many different genres. So that's the end of my presentation. So if you have any questions, you can just tell me here. Okay, we can just chat by email. So if you want to see my code and you see my use the pop now dataset, you can just email me. I can send to you. Any questions?
Okay. Well, first of all, thank you so much, Kia, for the wonderful presentation. Yeah, I do have a couple of quick questions. I know that it's set for you, and we a little bit ran over time. But first of all, anybody else has questions right now? Okay, so one thing that I wanted to ask you is how is the learning done? What is the loss function? What is the end-to-end?
Okay. So as you can see here, the transformer, the music transformer, actually we can just define it as the masking attention model with the absolute position encoding and the relative position encoding. So it means like the input will be a token plus the absolute position and the relative position. And then this is what we call x1. And x2 is the next token and next position, x3, for example. So they fit into the, for example, like the length will be like the 1024. So they fit into the 1024 length tokens. And then we can just like to let model to produce the 1025 one. So if you input the sequence from 1 to n, and the model will need to produce the n plus 1. So we use the cross entropy as a loss function in this kind of prediction. So because like the attention model is not like the RNN model, it can be computed in parallel. So it means like if you input the sequence from 1 to n, actually in the in the simultaneous time, actually you can do the prediction from 1 to 2, 1 2 to 3, 1 to 3 to 4, 1 to 3 4 to 5, and into 1 to n minus 1 in predicting the n. So it means like if you input in the infer test scale, it means like if you input the primer will be like for example 500. You just input the token into that, and then they can produce. Oh, then they might be this kind of token will be like 501, and then you input the 501 into that, and they can get the 502. Loop it again, and then we got the whole
Mhm.
sequence. So that's what you see about this kind of whole sequence here. Yeah. So this is the first question.
Right. Okay, great. So basically, you feed the future of the same sequence, a little bit like the RNN, but you can do this in much larger blocks.
Yes,
And
because like
then you train this on the whole corpus, right? That's
yes, yes.
um,
We can just slice the song into different lengths. For example, if you take the
mhm,
maximum length of the sequence to be like 2024,
mhm,
46, 48, sorry,
great.
and then 2048, and then you can just input the 2048 sequence, and then you
Mhm,
can do the prediction. But
right.
let's because let's not I mean like we did not know what the Google's music transfer truly does,
Sure.
but we just refer from many GitHub reports, and then we got this kind of thing. Might be the
Mhm,
answer. Yeah.
perfect. Yeah, I mean, I have a couple more of the technical questions, but yeah, so I think, the whole idea of having a less memory. Can you just remind us what was the L and the D in that? So you
Okay.
have the lengths of the attention layer, right? I mean, your
Yeah, yeah,
prediction,
yeah.
how big is the attention layer? You fix it ahead of time, right?
Yes. So the L is the sequence span. So it is the so if you take this kind of figure, the L is 4.
Right.
So like this is L.
So we're still limited by the size of how large the memory is, right? We will not be able to memorize like musical structure over symphony of 20 minutes, right? It's
Oh
still
no.
limited. Yeah, we're
But
still
like
limited to a
the
few bars, right?
yes, but it's very different because like in my research we use like the measure as the smallest unit, but in Google's like they use the token. So one token is not means like the one node or something like that.
Right.
It's like the
Okay.
one behavior. So maybe like
Hmm.
maybe like there's many token produce producing one node and duration. But like they take the sequence length of like 2048. Actually, in my experiment, if you feed into the 2048 sequence, the token sequence into the model after decoding, actually they will produce about like the 1 minute. So it means like
Right. I
actually you
see.
feed into 1 minute, so they will memorize like the one
Mhm.
minute length of
Mhm.
memory, and
Right.
then the attention model can memorize different parts of the 1 minute, so they can just
Mhm.
scratch or size what kind of things can be most different or like the second different in producing the next token. So that's the power of the attention model. That's what the recurrent network cannot do. Okay.
Right. Very nice. And the last question would be, oh, by the way, so this is the L and the D, just to
Yeah.
complete the first question, and the D was.
D was the dimension. Dimension is that x1 has a dimension about like 512 or
So it
like
depends on
110.
your representation, on your
Yeah,
embedding,
this is the
right?
hidden.
This
This is
this this is the hidden.
it's not the vocabulary size of the token. It is
Mhm.
the dimension of the QKV. Is
And
the
this
hidden
is
size.
this is your choice. This is your
Yeah, this is my
choice.
choice.
Right,
So
right.
we use the Google and I use also like the 512. There will be the enough for the training.
Right. And the last question, I will let you go.
Yeah.
Polyphony. I mean, it's kind of in the token representation, but can you say a word about how polyphony is represented? It's not explicitly represented, right?
Okay. Uh, so uh, so the the reason why this kind of token can produce a polyphony representation is because like they split it one node into three parts. The first part, if we delete the velocity, so it means like one node can be representation as the triplet list. Means like what time is on, how many duration we'll have, and what time is off, and then they scattered it into in the whole sequence. So like just like the behavior, it means like oh, at this time we should let one node on, at this time we should shift the time, and this time we should let something off. So this kind of thing, so it's just like the behavior of the like the MIDI control. So they can so it means like if we want to have the polyphony music, we just like take the many behavior of the on in the same time, and then we shift the time, and then
Mhm.
we can control what kind of time after what kind of what how many durations one notes off, another notes off. Example like take away. So that's why they can produce the polyphony music, but one of the critical disadvantages is that one token in his sequence cannot produce anything. So you cannot know that if we, for example, if we just pick the, for example, we have the length 1024. So if we just pick the 500 sequence from this kind of 124 sequence, so how many duration, how many time, how many nodes, you cannot know.
Right.
So that's not the physics thing. So at one space maybe like can equal to like the 30 minutes, and another space can be equal to like 24 minutes. So it depends on the complexity of your nodes in the score. So that's the one of things. So they cannot control the ends of the production. So it means like if we want to let model to generate, for example, like in the 1 minute, so they cannot promise that because they did not know what 1 minute means, the length of the how many lengths in different time. It's not it's different in on time.
Great. Okay, thank you so much. I think it was wonderful and very detailed and in-depth presentation. So I will yeah, post on Piazza your email contact. Is that would that be a good way? And also we can share the presentation. We have a Google Drive where we put all our lecture notes and yeah. Well, thank you again. And
So feel free to contact me if you have any questions for this kind of codes demo I can produce to you. Yeah.
okay, yeah, great. And hope to see you
Yeah.
like in CSD whenever things allow it. Okay.
Yeah. Okay.
All right. Thank you so much. And I'll also post the
Yeah.
recording. Yeah, yeah. Okay.
Okay. So I will send to you my slide here so you can just share with everybody.
Sounds good. Okay.